Now we will talk about differentials. Our function is y equals f of x here, as you can see, and the differential of this function y is denoted by dy, and it is given by this expression. You take the derivative of your function, you multiply it with the dx variable. You can see it as like this. The first derivative of y function is given as f prime of x. Now, if you solve for y dy from this equation, you obtain f prime x dx, which is the differential defined here. We will be using differentials to estimate the error in measurements. This is the usage of this dy quantities. So let's first see an example. How do we compute dy? Let's exercise on this. The function y is given as x to the power 5 plus 37x. So we want to compute dy here. That's why you will first take the derivative of this function, okay, which is 5x to the power 4 plus 37, and then you will multiply the first derivative function with the dx. This is your dy. And we want to find the value of dy now when x is 1 and dx is 0.2. Everything is given, just insert the values. 5 times 1 plus 37, and then this will be multiplied with the value of the dx, which is 0.2. So the result is 8.4. Okay, this is a very basic computation, as you can see. The more importantly, as I said, dy is used to estimate the error in measurements. So we need to observe what's going on with this picture. Okay, we have this point A here, and the image of it is f of a. A plus dx is the point here. Let's see where is its image. It is here, a plus dx. By the way, this difference between these 2 points is denoted by dx. It is the same as delta x, as this length is the difference of these 2 points on the x coordinate system. Okay, they are the same. Let's emphasize that. And now let's look at the vertical direction. You know, this is our tangent line. This is the tangent line, and as we discussed before, it is the same as the linearization function. That's why the difference in the values of the images on the tangent line, okay, this is what? This is L of a plus dx, and f of a is in fact the same as L of a in this case. So this difference corresponds, okay, here to here. This difference is delta L, where this difference is from here to here. We have the difference of the images. That's why it is delta y. Delta L is the difference of the images on the tangent line. Delta y is the difference of the images. So like this. And now we want to compare these two, okay? You remember that the linearization function is approximately the same as the values of the function. And when it comes to the difference of the values of your function, we denoted them by delta y, right? And the small change in x result in the change amount of dy in the linearization. You know, this is what we defined as dy above. Let me show you. Dy is f prime x dx. So this part is dy. That's why now I can tell you delta L is approximately as delta y. Why I can tell you this? Because as you can see from the graph, the difference between the images is approximately the same as the difference on the tangent line. So we can put this approximate sign here. And delta L is computed as dy. That's why the conclusion that we obtain here is dy is approximately the same as delta y. Okay, now we will be using this fact in the estimating measurements given in the next example. Okay, there is one more thing that I want to emphasize here. When we apply a small change in x, then the change in the linearization function is precisely dy. Okay, that's what we want to emphasize here. Okay, let's move on. Estimating with differentials. Again, these are all related to the picture here. F of a plus dx is what? It is f of a plus delta y. Why it is like so? Because you know delta y is what? Here, delta y is this difference. Let's write that difference once more. F of a plus dx minus f of a. Delta y is the difference of the images. And we want to solve this equation for this part. That's why it is given as delta y plus f of a, just like written here. And what we have emphasized here, delta y is approximately the same as dy. So these are approximately the same. That's why instead of delta y, if you write dy, you need to put approximately the same sign here. Okay, so the values of f at this increased point is approximately the same as the values of your function at a plus dy. We will be using this fact to solve the next example. Okay, look at the example now. There is a circle here, and the radius of this circle increases from a equals 10 to a equals 10.1. So there is an increase in the radius, infinitesimal increase. Use dA to estimate the increase in the circle's area. So circle's area is denoted by A. It is obviously pi r square. Okay. The area depends on the radius like that. And we want to do what? We want to estimate the area of the enlarged circle and then want to compare this estimation with the true value of the enlarged area. Okay. So how do we estimate it? As I said before, we will be using differentials to estimate in measurements. So if A is given with this formula, dA is A prime, the first derivative of the area function times dr. What is the first derivative of this function with respect to r? It is obviously, by the way, this is pi r squared. Let me fix it, not just pi r, of course, pi r squared. So the first derivative of the area function with respect to r is given like that. That's why the differential of the area function is this derivative times dr, just like written here, except that we evaluate it at the point A. Instead of r, we put A, okay? So this is the differential at some given point A. Now, what is A? A is given as 10. We inserted it, and dr is the very infinitesimal change in the radius, which is given as, so what is the difference here? Difference gives you the dr measure, like 0.1. Okay, we inserted it. So if you do this computation, you will find 2 pi meters square. This is the estimated change in the area, dA, differential. Okay, now let's look at this expression, A of r plus delta r. And we have just expressed or emphasized that f of a plus dx is approximately the same as f of a plus dy. So look at the corresponding version for this example. R plus delta r approximately the same as, instead of delta r, if you use dA, it becomes like this, just like here. Okay, so r is 10. The difference of the values of the radius is this much. This is the change in the radius. A of r is A of 10, and dA is computed as 2 pi here, so we insert them. Okay, after inserting all the values, you can easily, quickly do the computation. What is the area of a circle with radius 10? It is pi radius square, like that. So as a result, you find this value, 102 pi meters square. So this is the approximated value. Approximated value. This value gives us the estimation in the area when you enlarge the radius from this quantity to this quantity, the approximated enlarged area. And you can also compute the exact value of the enlarged area by using the area formula. You know, A of r is pi r squared, and our new radius is now the enlarged one. Enlarged radius. That's why let's compute the exact enlarged area. If you insert radius as this new value, you will find the result as this. And what is this? This is the exact value of the enlarged area of the enlarged circle, value of the area of the enlarged circle. Now you can compare these two values. One of is like that, one of is like this. So as a result, I can say that, okay, we computed this, the exact value, as this computed value here, 102.01. And we also give an estimation for the enlarged area of the enlarged circle. What was that? So in the first step, we find an estimation for this area of the enlarged circle as, where is it here? 102 pi. There's also pi here. And now if you compare these two, you see a very small difference between them. And this small error in our estimation occurs because of this difference between data A and the differential of A. There is a very small error. Small error between the exact value, which is this one, and the approximated value, which is this one. And this error comes from the difference of these two quantities. So I stop here. Thank you for your attention.